Sam, it's great to see you again. I'm going to jump right into it because you were just telling me something. We're like 10 feet away from each other, but we were just talking about something I didn't quite get. Where you were mentioning in the office HyperBeam nodes as bundlers. Can you help explain what the heck that means?
Yeah, for sure. So I think something that part of the community has started to understand at this point, but not everyone, is that Hyperbeam nodes are they implement AO core, but AO core is not just AO processes. It's a generalized language for expressing verifiable computation. So anywhere that you have a state transition, you should be able to generate uh, an AO core hash path and a commitment at the end to, hey, I did this computation and I got this result. And this is a globally applicable idea. You can do it, for example, or use it, for example, to create not just AO processes as we understand them today, but serverless functions. You can have a piece of Lua and you can say, hey, take this input and run this Lua on it, give me the result. Um, and you get that back with a hash path and the same verifiability that you get with a normal AO process. And so it's much, much, much wider than the traditional smart contracting system. I think if all of that didn't quite grok for you, perhaps one way of thinking about it is it's a decentralized physical infrastructure network operating system. It's like a hosting environment for many, many, many different services that are all in that sort of deep in category of like giving you the same verifiability properties as smart contracts, but doing something with physical infrastructure or that would traditionally be done off chain. So, one of the things that means you can use HyperBeam nodes for is filling in lots of the gaps in the permaweb infrastructure stack where we want a decentralized and verifiable solution for other things on the permaweb, not just AO processes. And one of those is bundlers. If you've been following along for a long time, you know that decentralized bundlers was always part of the plan. You can basically, in order to get scalability of Arweave base network, you add your data to other people's data alongside one another and you bundle it, and then you send just one base layer payment, and you can commit arbitrary amounts of data items underneath. And it makes it arbitrarily scalable, basically. But you need to have decentralized bundlers in order to stop the bundlers becoming a point of centralization or censorship. And yeah, we've had many bundling systems over the years, but none of them have been properly decentralized and trustless yet. But now we have that thanks to actually some work from the DHA team in building a bundling device into HyperBeam, or that runs on HyperBeam. HyperBeam is more like an app store. You can run many different devices on top of it. It's not like it's built in precisely. It's more like modules that you can grab from the permaweb to execute at different points in time. And well, now there's a module, a device we call it, that, yeah, does bundling functionality. And because of all of the work we already put into TEEs inside the system, you can add payments, which are all different modules of the stack. Now you can stack those things together and you can say, okay, well, I would like to pay a trustless, decentralized or distributed bundling node, which will upload the data for me to Arweave. And I can trust it because it's a TEE, and I can pay for it using whatever token is described in the payment devices, which is the same stack that we use for payments in HyperBeam nodes in general. So everything is modular, and so it all stacks together, and it's really allowing us to fill out all of the sort of loose ends in decentralizing the permaweb. So really, really very excited about that.
I like that. HyperBeam is an app store. I can understand that. I can understand that. Um, and this somehow connects to a popular topic among our community, which is Odyssey. Is that right?
Yeah, so the Odysee team have been helping. Basically, there's a channel of work ongoing to decentralize Arweave.net. And part of that is adding large amounts of data to caches and HyperBeam nodes, including Odysee data as well as Arweave data, so that we can decentralize access. Because then, where we're going next is you should be able to join a router in HyperBeam in the sort of AO core distributed network with all these different nodes running different services and the likes. and offer data that you can store it for a period of time, or you can cache it. That is, so it's not like Arweave storage where it's permanent and you're being stochastically checked to ensure that you have that data. You're not committing to having the data. You're just paid for providing the data on demand when the Arweave.net users ask for it, basically. And we in the middle, Forward Research has been subsidizing some level of data access for a while. We'll keep doing that, but the idea is to do that with a distributed network behind it. And that's how we get to, decentralization of Arweave.net, the data distribution in the system. And so the Odysee team have been building a bunch of different devices and parts of the stack to basically put that together. And at the same time, adding Odysee video data as existed previously off-chain into HyperBEAM nodes. And what that means is then other HyperBEAM nodes, if they want to, could take that and mirror it elsewhere. So you get a distributed cache of the data set. It's not fully decentralized, but it does give you, distributed and censorship-resistant access if people want to mirror it. So that's step one there. And then, of course, longer term, it's promoting certain parts of that to permanent and also allowing people to pay for short periods of data storage. And there's, of course, Load Network that's also building parts of that in HyperBEAM devices as well. Well, it's an app store, right? So, yeah.
Wow. Okay. That is cool. You just blew my mind. Related to AO, Arweave, the permaweb, we were talking about the ongoing way to communicate sort of the price of storage. All right. I mean, that's kind of what we're about permanence here. And we often find ourselves explaining how things are permanent. How is it possible that the data is permanent? Can you kind of just give us a refresher on why it is that we can so confidently say that when you upload to Arweave, your data is there forever, man?
Well, I would never say forever. The heat death of the universe
Heat death of the universe. Yeah, heat death of the universe. Yeah.
But we can't say engineered for the maximum possible time period. And that, what is the maximum possible time period? Well, it's introspectable. Anyone can look at it and they can assess the model for themselves and come to their own conclusion. We think it's extremely, extremely robust. And so how's it work? Well, first thing is, it's not magic. It's all very, to some extent, simple economics and mathematics, representing a risk model. So the observation is, hey, when you want to store a piece of data, there's a proof system for making sure the data is replicated. But on the economic side, you got to put aside some amount of tokens to pay for those replications over time. So the proof system can tell us who to distribute the tokens to, but you have to put aside the tokens. You have to choose how many to put aside in order for the system to work. So, okay, well, observation one. If you wanted to do this, one way that you could look at it is you could say, well, I'll just pay for like an extremely, extremely long period of time, say 200 years. And then, for a lot of people, that is essentially permanent. That's as far as they can, particularly if they're skeptical, they seem to think like, 200 years is so far out, it's basically forever. But when you do that, you see, okay, well, there's an interesting pattern in society, which is that the cost of data encoding and transfer of data over time is on a exponentially decaying slope. And there's a lot of reasons for this, but I think it's basically because human brains they're more effective, and now also computer brains, I guess, if they have access to more data. And so we're very, very incentivized to try and solve this problem or to optimize the provision of the service. And so then the question comes, okay, well, it happened in the past doesn't mean it's going to happen in the future, right? Well, maybe, but then if you look at it, what are the things that could stop it happening? So one, will that incentive run out? Doesn't appear so. Actually, it seems like, if anything, the sort of hunger for more data is like something like a constant. It doesn't seem to degrade over time. And this pattern goes back even to like writing on cave walls. You have to sort of, the categories of unit types don't elegantly line up, but you can see, okay, a certain amount of human labor went into carving that into the wall, right? So you can try and estimate how much value is that. And then you see, okay, well, how much value was required in order to encode the same amount of characters or the same amount of information into parchment, and then paper, and then typewriters, digital computers, printing press in the middle. You see it's just this very, very long trend where we appear to have an insatiable hunger for improving this. So that seems likely to continue. Then the question is, okay, what is physically possible? Right? Like, where are the limits of physics? And it turns out we're very, 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 very far away from them. Information encoding in a black hole is actually, as far as we're aware right now, the highest information density that is achievable by centimeter cubed. That's approximately 1 times 10 to the power 63 or 67, I forget, bits per cubic centimeter. We're at about 1 times 10 to the 26, 28 in production. So that's a huge, huge delta. So it looks very possible. It looks like we have all the incentive to do it. Okay, what would it mean? Well, if you put aside the capital to pay for 200 years worth of storage today, and the value of that capital stayed, let's say, evenly priced in consumer, or evenly valued in consumer prices, which is an asterisk we'll get back to, then you end up with a decaying cost of storage, which, as long as the rate of decay is higher than the consumption, so say you use 0.5% of the amount of storage cost that you put aside in 1 year, well, if the cost of storage in that time has actually decreased at a rate higher than 0.5%, you have more storage purchasing power at the end of that year than at the start. And so essentially what you're doing is kind of living on the interest, if you will, in the same way that a university endowment has an amount of principal and it generates interest on that, and it uses only the interest to pay for, student tuition fees, this type of thing. We're doing the same, except with storage. And what's really neat about it is that it doesn't need to go and invest in bet in the markets and try and be correct about, whether the NASDAQ is a good buy today or not. Instead, what it does is just wait for humans to make storage prices cheaper and then buy the same amount of the good. And subsequently, it has access to the yield, if you will, in storage purchasing power by just doing nothing. It's kind of cool. But then there's a question. Okay, so this makes sense as long as the storage purchasing power value preservation is in something that, actually does maintain its value over time. And all these things require token prices. Like, the reason this system is useful and powerful is because it makes that economic policy that I just described trustless. You don't have to trust me or anyone on the DHA engineering team or anyone else in the community that economic model will execute. You just go read the code and you can see it for yourself. That's really powerful, but means it needs to be decentralized. Okay, if it's decentralized, how do you hold value over time? You end up with tokens, basically. It has to be tokens. And it has to be a native token too. And those token prices are super volatile, like hyper volatile, sometimes up and down 60% in a single day. Extreme volatility. So then you get what is essentially a safety margin. And that's why we chose 0.5% decline in cost of storage rate as the expectation, rather than the actual rate in reality is like somewhere between 32 to 38% per year, depending on which year. If you look back in the last 50 is 37.5 approximately. So it's huge, huge safety margin. But the interesting thing is that safety margin is is part of the product, right? Like, if you lowered that safety margin, which you could, then actually you just make the service less reliable. And our observation from talking to people who are trying to buy permanent storage is there's no other thing in society that they can go to that offers this service in a reliable and robust way. So they would far rather have it be, actually work over time than have it be like a little bit cheaper, essentially. And so this has a very interesting property, which is that Arweave doesn't need to make profit from its users. It can give its services to people for the exact cost that it actually requires, is actually required in order to purchase the services, the storage from miners. yeah, and provide the product to them. This is very, very peculiar. And at the same time, it burns token time. So you put aside those tokens for 200 years, right? Well, during the time in between now and 200 years, that's even assuming that storage prices don't decrease ever again, which isn't going to happen. Yeah, for that period of time, those tokens are out of the supply. So it's a sort of deflationary effect on the system, which is really cool. Well, personally, I think. So it has a value accrual mechanism, which has no requirement on extracting profit from users. And that is really interesting because as a service, it means you just can't really compete with it on price. The only thing you can do is make a less reliable, less secure, or resilient service. It's super interesting. And well, I mean, yeah, I talked about it for, 15 minutes or something? I find it fascinating.
It
Um,
is super interesting.
yeah,
It is super interesting. I was thinking while you were talking, the next thing after AO, black holes. It's the only
black
logical
holes.
next step right there. Yeah.
Actually,
Okay.
DNA
Well,
data
Sam, I
storage.
don't want
That's
to
the
take up.
thing.
No, right there you go. Perfect, perfect data storage. I don't want to take up any more time. Really appreciate these check-ins we're having. Thanks so much, Sam. It was great to see you.
Thanks, Drew.